In this chapter, we focus on the carbon footprint modeling problem in modern supply chains. The goal is to quantify emissions across the network and then actively reduce them without breaking cost and service constraints. Our setting is a large multimodal network, where emissions come not only from transportation, but also from facility operations and supplier activities, spanning Scope 1, Scope 2, and Scope 3 categories. This slide describes the scenario and scale. Global Logistics runs 15 manufacturing facilities, 45 distribution centers, 200 suppliers, and serves 10,000 delivery locations across North America and Europe. The company aims for net zero emissions by 2030. That forces decisions about transportation modes, facility utilization, and supplier selection to be evaluated not just for cost, but for carbon impact and compliance. This slide previews the tier structure. We start with a multi-objective vehicle routing formulation with carbon budgets. Then we introduce a sweep heuristic, a Grasshopper optimization meta-heuristic, and neural architecture search for carbon prediction. We then use a digital twin to run continuous what-if analysis and real-time scenario evaluation. And we close with a value-aligned framework that enforces fairness and worker welfare constraints alongside emission reduction. Tier 1 builds a rigorous baseline, a multi-objective routing and network model that counts emissions directly from both transport and facilities. The purpose is to connect operational decisions to measurable emissions, not just to report a footprint after the fact. Operationally, this tier answers questions like which modes should carry which flows, which facilities should be active, and how do routing choices change total carbon while still meeting service needs. The model structures the network using sets of nodes, vehicles, products, time periods, and emission scopes. Nodes include facilities, suppliers, and customers. Vehicles represent different modes and types, such as trucks, rail, ships, and aircraft. Scopes capture direct emissions, energy-related emissions, and value chain emissions. Parameters include distances between nodes, emission factors by vehicle and product, vehicle capacities, and transportation costs by lane and mode. On the facility side, you include facility emissions by scope and time period, plus an overall carbon budget that cannot be exceeded. Finally, you set weights that control the trade-off between carbon minimization and cost minimization. The routing decision is a binary choice that indicates whether a vehicle travels from one node to another, carrying a given product in a given time period. You also track how much product is handled at each facility over time, and whether each facility is active in a given period. That last variable matters because an inactive facility should not generate facility emissions in the model. The objective combines two terms. One term captures total emissions. Transport emissions are distance times an emission factor, and facility emissions are counted when facilities are active. The second term captures transportation cost. The weights in the objective decide whether the model prioritizes carbon reduction aggressively or balances carbon and cost more evenly. The constraints enforce feasibility. Flow conservation ensures the network decisions are consistent with demand being served through active nodes. Capacity constraints ensure vehicle loads do not exceed capacity. A carbon budget constraint limits total transport emissions. Facility activation constraints enforce that you cannot route through a facility unless it is active. This figure shows the full supply network model and where emissions come from. The key point is that emissions are not only on the road. Facilities have their own operational emissions, and supplier choices influence upstream footprint. So the optimization must consider routing, facility operations, and supply configuration together. In the simplified example, there are 3 suppliers, 2 plants, and 4 customers, with trucks and rail available. Trucks have an emission factor of 0.8 kilograms of carbon dioxide equivalent per kilometer, while rail has an emission factor of 0.3. Using truck for shorter distances and rail for longer distances, the total transportation emissions are 245 kilograms of carbon dioxide equivalent per day. Facility emissions are 50 kilograms at plant A and 75 kilograms at plant B, totaling 125. The total daily carbon footprint is 370 kilograms of carbon dioxide equivalent. Tier 2 uses the sweep algorithm as a fast, geometric heuristic for routing. The core idea is to sort customers by angle around a depot and group nearby customers into routes. The carbon-aware version adds an extra decision. Choose the vehicle type and mode that reduces emissions for each route while respecting capacity. This slide shows the sweep idea visually. As a ray rotates around the depot, customers are encountered in angular order and assigned to routes. Operationally, this tends to create compact routes that reduce distance and also create consolidation, which often reduces emissions per delivery. This code section typically defines customer coordinates, demand, vehicle options, and emission factors. It also computes polar angles from the depot and sorts customers by that angle, which is the key pre-processing step in sweep routing. This part usually constructs routes by walking through the sorted list and adding customers until capacity is reached. In the carbon-aware version, it also computes route emissions under different vehicle types and selects the lowest emission feasible option. In the 6-customer example, the sweep produces 3 routes. Route 1 is depot to customer 6 to customer 1 and back, with distance 18.2 kilometers. Route 2 is depot to customer 2 to customer 3 and back, with distance 15.8. Route 3 is depot to customer 4 to customer 5 and back, with distance 12.1. With vans selected in all 3 routes, the reported emissions are 10.9, 9.5, and 7.3 kilograms of carbon dioxide equivalent, respectively. The total carbon footprint across all routes is 27.7 kilograms. Tier 3 uses the Grasshopper optimization algorithm. This is a population-based meta-heuristic designed for complex multimodal search spaces, where local heuristics can miss better global configurations. Each candidate solution represents choices like which facilities are active and what mix of modes is used across routes. This slide explains the high-level intuition. Grasshoppers represent candidate solutions that move through the solution space based on social interaction forces. Early iterations encourage exploration across many patterns, while later iterations concentrate around the best solution found so far. The position update rule describes how each candidate solution is updated relative to others and relative to the best known target. In spoken terms, the algorithm gradually reduces randomness, so the search shifts from exploration to exploitation, converging toward a stable low-emission configuration. This code part typically defines the representation of a candidate solution, the emission calculation, and the parameters controlling exploration, such as the decreasing coefficient. It also defines the social interaction function that shapes how solutions influence each other. This section usually implements the iterative update loop. Compute fitness for all grasshoppers, identify the best target, update positions, and enforce any feasibility repairs. Because this is an emissions problem, feasibility often includes mode share limits, facility activation logic, and capacity constraints. This part typically handles stopping criteria and convergence logging, such as reporting the best daily emissions at specific iterations. Operationally, these logs are what allow you to compare whether the algorithm is improving steadily or stagnating. In the reported example, initial random emissions are 2,847 kilograms of carbon dioxide equivalent per day. By iteration 100, the solution improves to 1,923. By iteration 300, it reaches 1,456. By iteration 500, it reaches 1,203. The final optimized configuration activates facilities 2 and 5, which are the lowest emission facilities in the example. The reported transport mix becomes 60% rail, 30% ship, and 10% truck. The reported total carbon reduction is 57.7% compared with the initial solution. Tier 4 introduces neural architecture search to predict carbon emissions quickly from operational features. The goal is not to replace the optimization model, but to add a fast predictor that can support rapid what-if evaluation. This matters when you need to screen many candidate plans and you cannot run a full simulation for each one. Neural architecture search explores many possible network designs automatically. The search space can include dense layers, recurrent layers such as long, short-term memory, and attention mechanisms. The system evaluates each architecture using prediction accuracy and also operational metrics like inference time, because a model that is accurate but slow is not useful in real-time decision support. This code section typically defines the search space and the training loop used to evaluate each candidate model. It also defines the evaluation metrics, such as mean absolute error for emissions prediction and the R-squared score for explanatory power. This part usually implements candidate generation and trial management. In the reported setup, the search runs 100 architecture trials on a dataset with 50,000 historical records. The system logs the best performing candidates and keeps a record of the architecture and hyperparameters for reproducibility. Here you typically see training and validation logic for each candidate model. A key operational requirement is robust generalization, because the model must predict emissions across different seasons, traffic conditions, and utilization levels. This section typically covers model selection and export. Pick the best architecture based on accuracy and latency, and prepare it for deployment. Operationally, this is where you ensure the model can be embedded into planning tools without adding unacceptable compute cost. The best architecture reported is 4 layers: a dense layer with 128 units, then a long short-term memory layer with 256 units, then a dense layer with 64 units, and finally a single output layer. Reported mean absolute error is 45.3 kilograms of carbon dioxide equivalent. The R-squared score is 0.94, and inference time is 12 milliseconds. In a real-world example with total distance 2,450 kilometers, truck share 40%, rail share 60%, 3 active facilities, and 78% capacity utilization, the model predicts 1,847 kilograms with about 45 kilograms uncertainty. The actual measured value is 1,892 kilograms, corresponding to 97.6% accuracy. Tier 5 introduces a system of systems digital twin that keeps a live virtual replica of the supply network. The twin supports continuous what-if analysis and dynamic optimization rather than static monthly reporting. The goal is to make carbon reduction an operational control loop. Observe, simulate, decide, and adjust. The digital twin is multi-scale. At the microscopic level, it simulates individual vehicle routes and facility operations at roughly 1-minute resolution. At the mesoscopic level, it simulates regional flows and mode selection at roughly 1-hour resolution. At the macroscopic level, it supports strategic design choices such as supplier selection on a daily cycle. This code section typically defines data ingestion and synchronization, turning operational telemetry into a clean state for simulation. It also defines how scenario alternatives are generated, such as changing route assignments or shifting mode shares. This part usually runs the optimization cycle on a schedule, for example, every 15 minutes. It evaluates candidate actions, checks feasibility, and outputs recommended changes that can be deployed immediately. Here you typically see the what-if framework. Compare scenarios such as route optimization, renewable energy scheduling, and facility rebalancing. The key is that the twin reports both carbon and cost impacts, so decisions remain economically viable. This segment usually handles logging, dashboards, and governance. It stores scenario results, carbon deltas, and the rationale for each recommendation. That traceability is essential when carbon decisions must be audited and justified to regulators and customers. In the European network example covering 12 countries, the digital twin runs a 15-minute optimization cycle. Current operations show a daily carbon footprint of 45,230 kilograms of carbon dioxide equivalent, with transport split 78% truck and 22% rail, and average facility utilization of 67%. Scenario B, route optimization, projects daily carbon of 38,950, which is 13.9% lower, and shifts the transport split to 62% truck and 38% rail, with an additional cost of 2.3%. Scenario C, renewable energy scheduling, projects 41,680, which is 7.9% lower, by shifting facility operations into solar peak hours from 10 in the morning to 3 in the afternoon. The digital twin recommends deploying Scenario B immediately, achieving a 6,280 kilogram daily reduction, and predicting 2.29 million kilograms annual savings through continuous optimization. Tier 8 adds stakeholder values and ethical constraints. Carbon reduction is not treated as the only objective. Instead, the system must also protect community health, worker security, and environmental justice. And it must reject strategies that violate hard constraints. The framework is described as layered, a constitutional layer of non-negotiable ethics, a stakeholder layer balancing communities, workers, and shareholders, a temporal layer balancing short and long horizons, and a justice layer ensuring impacts are distributed fairly. Operationally, this prevents the common failure mode of improving emissions by exporting harm to vulnerable groups. This code section typically defines stakeholder weights and the hard constraints, such as maximum allowable job losses or community emission caps. It also defines how the system computes a combined value-aligned score from multiple metrics. This part usually evaluates multiple scenarios under the same scoring system. The algorithm first checks hard constraints. Any scenario that violates a hard constraint is rejected regardless of how large the carbon reduction appears. Here you typically see how community impacts and worker impacts are quantified and normalized. That quantification is what makes ethics operational. Values become measurable constraints and score terms rather than vague principles. This segment often handles optimization or search over policy settings, such as how much to shift modes, which facilities to activate, and which suppliers to prioritize. The output is not just a plan, but a plan with an explanation of why it satisfies the value hierarchy. This part typically produces reporting and decision support artifacts, dashboards, score breakdowns, and constraint satisfaction summaries. This is critical for stakeholder governance because carbon decisions must be communicated transparently. This final code section usually ties the system into ongoing monitoring, ensuring that the operational plan continues to satisfy ethical constraints as conditions change. It also defines re-optimization triggers when emissions, costs, or impacts drift beyond acceptable bounds. In the value-aligned example serving 3 communities, stakeholder weights are community health 0.35, worker security 0.30, shareholder returns 0.15, and environmental justice 0.20. Scenario A achieves a 28% carbon reduction, about 450 kilograms per day, but causes 120 job losses and violates a hard worker constraint, so it is rejected. Scenario B achieves a 22% reduction, about 354 kilograms per day, with moderate air quality improvement and a net gain of 30 jobs through retraining programs. It is fully compliant and receives a value-aligned score of 0.78, so it is selected. Scenario C achieves only 8% reduction, about 129 kilograms, but has higher worker security. It remains compliant, but scores lower at 0.52. These questions test whether you can implement the core ideas. You practice formulating a carbon-aware routing model with facility emissions and mode emission factors. You also practice implementing a carbon-aware sweep heuristic, designing a Grasshopper optimization run, and interpreting convergence and designing a multi-scale digital twin update cycle. To close, carbon footprint modeling is only valuable when it changes decisions. You need a model that ties emissions accounting to routing, facility activation, and mode choice under explicit carbon budgets. Heuristics and meta-heuristics provide scalable improvement. Learning models enable fast prediction, and digital twins enable continuous re-optimization. A value-aligned framework ensures emission reduction remains fair, socially feasible, and implementable.